Hello, everyone. I'm going to present this work due domain closed loop learning for Sparse-view CT reconstruction. Note that I'm not the author of this work. I stand for Igor to present this work, and the authors are from Jianhua group and in the Department of Biomedical Engineering in Southern Medical University, Guangdong Province of China. Here is some information about this team. The top picture shows the school, and the following picture shows some members of this research team. And this work was supported in part by NSFC grants and the National Key R&D Program of China. So this presentation consists of 4 parts, including background, methodology, experiments, and conclusion. So the first part is about the background. By increasing the interval between different exposure angles in the scanning process and reducing the sampling rate of projection data, Sparse-view CT imaging can significantly reduce the radiation dose of CT scanning and has great potential in the future development of CT imaging. However, the reduction of the data sampling rate brings great challenges to the reconstruction of high-quality images. As shown in the figure, the top row represents the CT imaging under the normal sampling rate, and the lower line represents the sparse-view CT imaging. The exposure interval of sparse-view scanning is larger than that of full-view scanning. As a result, the artifact and noise in the sparse-view FBP reconstruct CT images are obvious and seriously affect subsequent diagnosis. Therefore, new sparse-view CT reconstruction algorithm are desired to reconstruct high-quality images and reduce the sampling rate of projection data. So the development of deep learning offers new possibilities for sparse-view CT reconstruction. Many studies have shown that using deep learning for sparse-view CT reconstruction can obtain excellent reconstruction results. In general, CT reconstruction algorithm based on deep learning can be divided into 3 categories. The first category trains a network mapping from low dose data to normal dose data in the image domain or projectional domain to improve the quality of image reconstruction. Generally, this kind of method still uses the traditional FBP algorithm for reconstruction, and it's convenient and efficient, and can directly introduce the excellent networks in other computer vision tasks to CT reconstruction tasks. However, these methods only deal with single domain images and lack the constraint of either project domain or image domain. The second type is deep iterative reconstruction. This kind of algorithm combines iterative algorithm with deep learning to reconstruct high-quality image by learning relevant prior information or hyperparameters. These hyperparameters are difficult to adjust manually. However, it does not fall outside the category of iterative algorithm, and its essence is still iterative algorithm, which does not overcome the inherent defect of that is the time-consuming problem of the iterative process. The third category builds a projection to image reconstruction network. Through a lot of parameters with sufficient training, the network can directly learn mapping from sparse-view projection to images without artifacts. An algorithm of this type uses the network to forcefully learn the relationship between two domains. It is difficult to reconstruct high quality images from CT images because of lack of physical constraints. In addition, since CT images and projections have larger dimension, a very large network is required to learn the relevant transformation, which is very difficult. So the entry points for different types of algorithm are different. Better reconstruction quality can be achieved by carefully designing networks and adjusting parameters, but there are some shortcomings in different types of algorithms. How to combine the advantages of different algorithms and overcome the corresponding shortcomings is a topic worthy of research. So this is about dual learning. Unlike traditional supervised learning or semi-supervised learning, is a new learning paradigm that forms a closed loop system by creating a dual problem of the primal problem. Through this closed loop system, the primal dual and the dual problems can mutually promote learning from each other, resulting in better learning. Dual learning has been a great success in natural image processing. For example, in the image super resolution task, primal task is to learn the mapping from low resolution image to a high resolution image. And the dual task is to learn the mapping from the high resolution image to the low resolution image. The image super resolution task can be improved by adding primal loss and the dual loss and learning two mapping simultaneously. So in Sparse-view CT reconstruction task, iterative reconstruction algorithm can often provide better reconstruction quality than a non-iterative algorithm. The iterative algorithm reconstruct image by continuously forward projecting the reconstructed image, compares the estimated projection with the measurement data, and then reconstruct the corresponding error image to update the target image. Advantage of iterative reconstruction is that it exploits the consistency constraint between the reconstructed image and the original measurement data. That is the projection data derived by forward projecting the reconstructed image should match the measured projection data, and thus creating a closed loop reconstruction system. Comparing iterative reconstruction algorithm with dual learning, the authors found that it has a great similarity that a closed loop learning system is conducive to the solution of the problem. Based on this observation, this study intends to construct a closed loop learning reconstruction network for Sparse-view CT reconstruction. It is called CR Recon. So this slide shows the overall framework of CR Recon. It contains two mappings. One mapping learns the transformation from projection to image, and the other mapping learns the transformation from image back to projection. So there are three modules in the primal mapping: a projection domain subnetwork, a differentiable back projection module, and an image domain subnetwork. For subnetwork G1, it first contains a B-spline interpolation layer, and is followed by a convolutional neural network module as a key part of this of the overall network framework. This subnetwork directly restores missing projection data and plays a key role When the sparsity level is high, it's difficult for the projection domain network G1 to recover the missing data, resulting in an unclean removed of artifacts and noise in the reconstructed image. Therefore, an image domain network G2 is required to further remove the residual noise and artifacts in the reconstructed image. Since each subnetwork needs to be optimized simultaneously in the training process, a differentiable backward projection model is needed to fit the error in the image domain to the projection domain. In this study, authors built in FBP algorithm based on PyTorch. Since this research is mainly based on the simulation pairing data, and the authors use the MSE loss for training. In the dual domain mapping, only one forward projection module BP is needed to achieve the consistency constraint between the reconstructed image and the measured data in principle. However, even if the most advanced distance-driven forward projection algorithm is used, projection error is inevitable. Consequently, even if the reconstructed image is accurate enough, the estimated projection obtained by forward projecting the reconstructed image is still not consistent with the original measurement. The existence of dual mapping may degrade the quality of the reconstructed image. To solve this problem, the authors add an image domain subnetwork G3 to the dual mapping. In the process of error backpropagation in the projection domain, the subnetwork G3 can learn not only the reconstruction error caused by data and the sampling, but also the error caused by forward projection. Due to the existence of simulation pairing data, they use the forward projection data and the full view projection to construct the projection domain loss, and hopefully getting better learning performance. In this study, MSE loss is used in both primal and dual mapping. The total loss is the weighted sum of both terms. As shown in the figure, lambda is set to 0.8 empirically. So the authors verified performance of the proposed CR recon using through a series of experiments. The data used in this experiment are AAPM low-dot-CT challenge data. Over 10,000 slices from 34 patients are used for network training, and over 1,000 slices from 6 patients for validation and testing. The authors project image to the to obtain the simulation full view fine beam projection data. The geometry parameters are set as shown in this slide, and some implementation details for training are shown in this slide. And in the proposed CR recon, the authors add an image to projection mapping to the primal mapping and form a closed loop reconstruction system. To illustrate the effectiveness of this approach, a set of different combinations of G1, G2, G3, and the forward projection module FP are compared. The experiment is experiment 1 is similar to the basic deep learning based Sparse-view CT reconstruction algorithm, which uses an image domain network to improve the noise and artifacts to remove the noise and artifacts in the image reconstructed with FBP. And the second experiment used both projection domain network and image domain network, which is consistent with the primal mapping in CR-Recon. And the second experiment as an FP module on the baseline of the basis of experiment 2 to realize the consistency constraint between the reconstructed image and measured data. In this experiment, they didn't consider the forward projection error, and compare with the third experiment, experiment 4, uses image domain network G3 to learn the errors generated in the forward projection. And the experimental results are shown in the figure. Compared with the experiment 1, the reconstructed image quality of dual domain network is better than that of image domain network only. And compared with experiment 2 and experiment 3, increasing the consistency constraint between the reconstruct image and the original measurement data. Even without considering the forward projection error, they found that the quality of the reconstruct image is still improved. So compared with the third experiment, the fourth setting with its methods consider the error caused by the forward projection, and the experimental results show that the reconstruction quality is further improved after considering this forward projection error. So furthermore, they compare the CR-Recon network with more existing methods, including FBP coordinates, Redsian, FVV tensor, framing units, D-dense net, and they also applied FBP coordinate to projection data and use FBP to reconstruct the restored projection. The experimental results are shown in the figure. It can be seen that the proposed network is superior to other networks in edge elevation and artifact separation. The relevant quantitative analysis is shown in the red table. It can be seen that the RMSE of this network is lower than other networks, and the corresponding SM is nearly 2 percentage points is higher than that of other best networks. It can be noticed that the proposed CR-Recon can obtain better reconstruction quality in Sparse-view CT reconstruction task. So here is the conclusion. They presented a closed-loop learning model for Sparse-view CT reconstruction. The proposed method constrains 2 learning mappings. Primal mapping learns the transformation from Sparse-view projection to reconstructed image, and including image domain network, projection domain network, and differentiable back projection model. And dual mapping learns the transformation from the reconstructed image back to the projection. In order to overcome the error caused by the forward projection, a subnetwork is added in the image domain. The proposed CR-Recon uses the consistency constraint between the reconstructed image and the original measurement data, which has been greatly successful in iterative reconstruction algorithm. In this learning framework, the reconstructed image quality is also improved. And the experiments show that the proposed framework can produce excellent reconstruction results than the some competing networks at this stage. In the future, the authors will verify the effectiveness of the proposed network framework proposed methods through more experiments, including testing with different types of data sets, testing at different sparse levels and with different subnetwork architectures. That's all about this presentation. Thank you.